There we go. Okay, gang, welcome back. Today we have, happy Saturday. Today we're going to do a little bit of an extra lecture. So my Tuesday, Thursday classes, sections 008 and 009. You guys lost a day last week due to Veterans Day, and that's fine, of course. Veterans Day is a great holiday. We should celebrate and honor the people who fought for our country, whether you agree with the wars or not. Those people have made tremendous sacrifices and they deserve our respect. The mathematics also deserves our respect, so we need to make sure we're not losing time here in a way that we can't really afford to. So if you're in the Tuesday, Thursday class, think of what I'm recording for you right now as the Thursday lecture. If you're in the Monday, Wednesday class, think of this as kind of a supplemental lecture. Both of your classes, the Tuesday, Thursday groups and the Monday, Wednesday groups, have an exam next week. If you're Monday, Wednesday, your test is scheduled for Wednesday. If you're Tuesday, Thursday, your test is scheduled for Thursday. And I don't want to be dropping new material on you at the start of the week that you'll be tested on later that same week. That just doesn't feel fair. So I wanted to record this lecture ahead of time, give you the opportunity at least to expose yourself to the material, practice some of the problems. So please treat this the way you would treat a regular lecture. Obviously, you can't really ask questions here, but I'm going to go slow and be very methodical. What we're going to be talking about today are logarithm equations or logarithmic equations, however you want to say it. Those are kind of the counterpart to the exponential equations that we've been dealing with. So an exponential equation, remember, is an equation where the variable you're trying to solve is stuck up in an exponent. A logarithmic equation is an equation where the variable you're trying to solve for is stuck inside a logarithm. So let's do it. Now, my wife is out of town this weekend, and that means I'm on full-time baby duty. So you may hear my son, he's in his little swing in the other room, but if I have to pause from time to time, I'll stop the recording. It might seem a little choppy, but that way you'll have some cohesion. And that's it, that's the plan. So here we go. This is MAC 1140, all sections, which are all pre-calc. And this is the date today is the 13th of November. Today. This is the second half of section 4.5. So we're talking about logarithmic equations. That's section 4.5. I think it was like a part 2. All right, so we talked about exponential equations last time. That is also section 4.5, but today we're talking about logarithmic equations, which is the latter part of 4.5. All right, I just want to make sure I have all my video controls down here set up so we can pause if we need to. All right. So recall an exponential equation, just a quick recap, is an equation where the variable, at least one instance of the variable, is stuck in the exponent. I think I do have to go deal with that. I'm going to summarize the results from last time when we get back. Okay, we're back. He was not loving the swing, so we've got him set up in his little play mat down here. You may hear a bit more of him, but I'll be mindful and pause if we have to. So an exponential equation is an equation where the variable is in an exponent. The procedure to solve these first, we want to isolate the exponential term. So, you've got an e to the x or a 2 to the x or a 5 to the x minus 1 somewhere in your equation. That's what makes it exponential. You want to get that piece alone on one side. Then you have to use that new operation take logs, and you can use whatever base you want, right? I use the natural log when I solve exponential equations pretty much all the time, because if you're going to put it into a calculator to get a decimal approximation, you would need to convert like a base 2 log or a base 5 log into either a natural log or a common log anyway. So I opt to take the natural log in step 2. And then you, along here, we'll say use properties of logarithms to get the variable down. Down meaning out of the exponent. And then you solve the resulting equation. All right, once the variable is down out of the exponent, usually you'll be dealing with a linear equation, or certainly it will no longer be an exponential equation. That's what that operation of taking logs does. And we saw plenty of examples of this. If you don't remember this, you want more practice with this before starting on logarithmic equations, I strongly recommend you go back to the previous video where we solved a bunch of exponential equations towards the end. Logarithmic equations go largely the same way. You're going to isolate the logarithm term. Then you're going to apply some new operation, kind of like the backwards version of taking logs. You're going to use properties of logs and exponents to get the variables out of the logarithm. And then you're going to solve the resulting equation, very similar. I remind you that before this first step, sometimes you want to do some factoring. We saw some more kind of, I don't want to say complicated, but more involved exponential equations where we had to maybe make a substitution like u equals e to the x or factor. The same will be true of these logarithm equations. Sometimes isolating the exponential term isn't as simple as like just dividing over or adding a constant. Sometimes you do need to be a little bit mindful of step 1. But this is it. This is how we solved exponential equations. And I just wanted to recap this because you'll notice a similarity between this and how we solve logarithmic equations. Really quick, just for gits and shiggles, I think it would be wise to do one quick example here, kind of get you back in that right headspace. So to that end, let me find one to fiddle with. Here's something. Well, let's see. Yeah, how about this guy? How about 50 over 1 plus e to the negative x equals 4. We want to solve for x. So this is an exponential equation because if you hunt around in this expression for the variable, there it is, it's in the exponent, right? This base here, this is a base e, but it could be a 2 or a 10. The procedure would be pretty much the exact same. So if I follow my kind of procedure here, we should try to isolate the exponential term. I want to get this thing alone on one side somewhere. Then we're going to take logs and solve the resulting equation. Hold the purple here for the solution. Since this 1 plus e to the negative x is downstairs, the first thing I'm going to do is multiply on both sides by that whole quantity. I'll write it out. All right, so that's multiplying on both sides by 1 plus e to the negative x, which is going to get rid of the denominator over here. It's going to move that term to the right-hand side. So the left-hand side is now just 50. And over here I have 4 times 1 plus e to the x. I'm sorry, e to the negative x. Again, I'm still working on step 1. I'm trying to isolate the exponential term. I can divide both sides by 4. And I'll get 50 over 4 equals 1 plus e to the negative x. 50 is divisible by 2, but it's not divisible by 4. So this isn't going to be a whole number. but 50 is 25 times 2, 4 is 2 times 2, so I can simplify on the left-hand side. Right, this is 25 over 2 equals 1 plus e to the negative x. I'll put a little divider here so I can come back up to the top of the page after this next line. Subtracting, oh, let me just come up now. So now I subtract 1 from both sides, and I get 25 over 2 minus 1 equals e to the negative x. So kind of everything over here, this is step 1, and this is the result of finishing step 1. I have the exponential here on its own, isolated. So we've isolated the exponential term. My next step would be to take logarithms. And even if this wasn't a base e exponential, I would use the natural log, especially since it's the base e exponential, we want to use the natural log. But even if it wasn't, that's what I would use. So now we take logs. I'm going to take the ln on both sides, or of both sides. And that's going to give me the ln of 25 halves minus 1 equals the ln of e to the negative x. And remember, it's just like taking square roots on both sides or anything like that. We're not multiplying by ln, we're putting both sides inside the ln function. So make sure you use these parentheses. From here, the left-hand side is going to stay like this, but the right-hand side, there's a property of logarithms. This power could come down. I could write this as negative x times the ln of e. The ln of e is 1, remember. So that would just be negative x. Or you can use that kind of characterizing property of the natural log, that the natural log of e to some stuff is always just that stuff. However you think about it, you're going to get the ln of 25 halves minus 1 equals negative x. And now to get x alone, we just multiply both sides by negative 1. We got to get rid of that negative. So this becomes negative ln of 25 halves minus 1 equals x. And that's job done. Not bad at all. All right, yeah, equation solving like this could very well show up on your next test. There's only so many sections on this test, fairly short collection of sections. So I would expect at least one exponential equation, at least one logarithm equation. If we wanted to approximate this number as a decimal, we can do that. So remember, this here is what we call the exact solution in terms of logarithms. And often it's the case that we want both an exact solution and a decimal approximation, because this number is kind of hard to say how big this thing is, right? 25 over 2, how big is that? 26 over 2 would be 13, right? So this is just a little smaller than 13. So the thing inside here is probably a little smaller than 12. How big is the natural log of 12? That's not super obvious. Bigger than 1, definitely. Bigger than 2. Yeah, bigger than 3? I don't know. I'm a negative here. So it's somewhere around negative 3-ish, but not at all easy to say without the calculator. So glad that emulator I just started usually takes a minute. There we go. How we would enter this. This is the negative. Down here for the negative, not this. This is subtraction. Calculator thinks of those differently. Negative ln of 25 divided by 2 minus 1, all inside the natural log. You want to be careful with your order of operations, right? This is, if you want to put parentheses around 25 over 2 to make yourself feel more comfortable, that's fine. But the calculator will do division before subtraction, so this will be okay. So what do we say? About negative 3, right? Negative 2.44, not bad. So this is your exact solution. The approximate is x approximately equal to shaky equal sign negative 2.44, say 23. Up to you where you want to round, unless the problem says round at this particular decimal place. All right. Study this procedure. Make sure you're comfortable with it. You have plenty of practice problems in the homework. Work those problems. Work at least some of the exponential problems before starting on the logarithm problems. Okay, I'm going to switch over here. We're going to start talking about logarithm equations now. So it's just a little recap on exponentials. Let's do it. This something? All right, that's my little man. Okay. So logarithmic equations. Like I said, this is an equation where your variable is trapped inside the logarithm. And the new operation that we use here is exponentiate. So to get a variable out of a logarithm, you're going to exponentiate on both sides. And this word exponentiate means to put in the exponent of, and then you pick your base, right? What's going on here, remember sort of defining property of logarithms. We use the fact that the base a log of a to the x is always equal to x, or the fact that the ln of a to the x is equal to x times the ln of a. These are the tools we use to solve exponential equations. Right? So when we take logs on both sides, if there's an a to the x, when you take the base a log, if the bases match, you just get x. If you take the ln of both sides and on one side you have an a to the x, then that x can come down. And that was one of our properties of logarithms. These are sort of the two rules that allow us to solve exponential equations using logarithms. There is another version of this guy. If you raise a to the power of the base a log of x, this is equal to x. And this is what we're going to use to solve logarithmic equations. Unfortunately, there isn't something quite as nice and clean as this that has an exponential version, right? What that means is you're going to have to pick your base when you exponentiate. So the fundamental idea here, let me just show you an example. If you have something like the, let's say, log base 2 of x equals 7, and we want to solve this for x, this would be a logarithmic equation because my variable is stuck inside of a logarithm. And after you've isolated your logarithm, this is generally what you're going to be looking at, something like this for even more complicated logarithmic equations. To solve something like this, we're going to use this property. And the way you get this property involved here is by doing this operation. So the left-hand side of my equation is the base 2 logarithm of x. And what I'd like to do is get rid of that log. To get rid of that log, I'm going to exponentiate both sides using the same base as that logarithm, right? I know that if I put both of these sides, in particular the left-hand side, in the power of 2, then what I would have, so here's the step, we are exponentiating, and I'm using base 2. I'll get 2 raised to the log base 2 of x equals 2 raised to the 7. So you put both sides in the exponent of 2. And now that left-hand side looks very much like the left-hand side of this property. So 2 raised to the log base 2 of x is just x. And so we get x equals 2 to the 7. And 2 to the 7, you may know off the top of your head, you may not. 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64. So 2 to the 7 would be 64 times 2 is 128. And that's it. That's your solution. Sometimes you'll be able to take this answer and simplify it to an integer, but often we'll just leave it in this form. Either one would be acceptable. That's the basic game. That's it, right? This works because exponential equations are one-to-one, so you can compose on both sides of an equation with an exponential, and the equation will stay the same. The solution set will stay the same. In other words, this operation, exponentiate, no matter what base you're using, as long as it's a positive base, not equal to 1, will preserve the solutions. But that's the big step here. So just like taking logs is the big step to solving exponential equations, exponentiating is the big step to solving logarithm equations. And the procedure, the more general procedure here for solving logarithmic equations very similar to solving exponential equations. First, you want to isolate the log term. So that's the logarithm that has your variable in it here that was already isolated. Then you want to exponentiate. So that's that new operation. And here, we have to use the same base as the logarithm. Exponentiate on both sides using the base of the log term. So whatever logarithm it is you're trying to get rid of, like in this first example, I was trying to get rid of a base 2 logarithm. Whatever that base is, that's what you need to exponentiate by. And notice this is different than raising both sides to the 2, right? I didn't square both sides. That's what raising both sides to the 2 would be. That's why we use a different word, exponentiate. And then, you know, the properties of logarithms, you will end up with your variable down. You'll end up with your variable out of the logarithm. You solve the resulting equation. Which most of the time will be a linear equation. All right, that's it. That's the whole game. It's really not that bad. Let's look at some examples that aren't quite as trivial. All right. Yeah, we'll start with 2 nice simple examples. Just barely more complicated than the one we did. I recommend, after I write these down, pause the video for a second and see if you can solve these on your own, because these are very, very similar to what we just did. So first, we're going to solve the equation, the natural log of x is equal to 8. And then we're going to solve the equation, base 2 log of 25 minus x is equal to 3. All right, so I invite you to pause the video now and take a shot at solving at least this first one. All right, whether you paused or not, let's see how to do this. So the log term is already isolated, right? I've got the natural logarithm of x on one side and just a constant on the other. So I will exponentiate. And I'm going to use the same base as that logarithm. That's a natural log, so its base is e. Hey, baby, it's okay. Excuse me. All right. So remember what this word means. We're going to exponentiate on both sides using the base e. That means we're going to put both of these sides in the base, in the exponent of e. So what do I get? I'll get e raised to the ln x equals e raised to the 8. And then on the left-hand side, e raised to the ln x, the thing I get when I exponentiate, that's just x. And e to the 8 is e to the 8. If you want to approximate e to the 8, you can. On your calculator here, like I said, I don't have a TI-30 emulator. I haven't been able to find one yet. If you find one, let me know. I'd love to have one. But we can type second and here, divide to get e, and the caret to get into the exponent, and then 8. About 2,981-ish, around maybe to the third decimal place, second decimal place. So that's 2980 point. Yeah, second decimal place would be 0.96. We'll just call it that. Fair enough. So this is the exact answer, e to the 8. And this is the approximate answer. The second equation is also simple-ish in the sense that the logarithm is already isolated. Now, 25 minus x inside, don't be afraid of that. Also, don't try to do anything silly with that. So quick note. Log 2 of 25 minus x is super duper not equal to log 2 of 25 minus log 2 of x. This never works. Don't try to split up logs like that. Remember, the previous section was all about properties of logarithms. Those things that I showed you that you can do, like turning multiplication inside the log to addition outside the log, those are the only things that you can do. Don't try to do other things besides those, right? I promise you, if there were other cool things like this that worked, I would have shown them to you. So please don't fall into that trap of trying to split this up over the subtraction. It just never works. Nothing like that ever works. What does work, if I start here, I'll just rewrite the equation. I've got log base 2 of 25 minus x equals 3. If I could just get rid of the logarithm, this would be an easy equation to solve. And the trick to getting rid of logarithms is exponentiation. So we're going to exponentiate using the base of that logarithm, which is base 2. And I'll write down what we get there. That's 2 raised to the base 2 log of 25 minus x equals 2 raised to the 3. So it's simple. Both sides just go into the exponent of 2. On the left-hand side, 2 raised to the base 2 log of some shit is always just going to be that shit. So the left-hand side is just 25 minus x. On the right-hand side, 2 to the 3 is 8. A bunch of ways you could solve from here. I think what I would be inclined to do is add x to both sides, then subtract 8 from both sides. But what I think everybody else would probably do is subtract the 25. So this is negative x equals 8 minus 25, which is negative, what's that, negative 17. And then you get rid of the negative, and multiply or divide by negative 1, however you want to think of it, and x is 17. Now, one important feature of exponential functions, or logarithm equations, not exponential functions. In fact, here, call it a warning. Exponential functions don't have any domain restrictions, right? The domain of e to the x, 2 to the x, 10 to the x, whatever, all real numbers. Logarithm functions do have domain restrictions. So you should always check your answers to logarithmic equations in the original expression. Remember, you cannot plug a negative into a log, right? You can plug negative numbers into this expression, but you need to make sure the inside of the logarithm is not negative, right? So if I plug negative 2 in here, that's fine, because 25 minus negative 2 is 27, right? Which is positive, that's no problem. But if I plug 30 in here, then this would be 25 minus 30, which is negative 5 inside my logarithm, and that would be undefined. So you need to be careful that whatever solutions you're getting, your original equation is defined at that value. If it's not defined at that value, if you get the log of a negative number or the log of 0, then that's what's called an extraneous solution. You just throw it away. This first guy, I didn't bother with that. E to the 8 is positive, and this is just the ln of x equals 8. You can check very quickly that if you plug in e to the 8 here, you do get a true statement, right? The ln of e to the 8 is 8. And this number is most definitely positive. There's nothing else going on inside that log to worry about. Here, when I check, just being careful, I get the base 2 of 25 minus 17 equals 3, which is log base 2 of 8 equals 3. And this is a true statement, right? You've practiced evaluating logarithms enough to know that the base 2 log of 8 is 3. And crucially, the inside of the log, after you plug in, is positive. All right, so that's my answer, 17. It's okay. It's okay. He's starting to tease. All right, let's try a few more complicated logarithm equations. We'll start with maybe, yeah, this guy looks good. 4 plus 3 times the log in the base of 2x equals 16. So I'd like to solve 4 plus 3 times log of 2x equals 16. Remember, when you see log written without any base, that means the base 10 logarithm. That's the common logarithm. Just like the square root symbol without anything is the square root with 2 as the denominator of the power. Here, log without any base written is automatically assumed to be the base 10 log. Okay, switch to purple. Let's go away. So first, I need to isolate the log term, right? This has not already been done for me here. So the log term is the log of 2x. I want to get this piece alone. So I need to subtract the 4, then divide by 3. (16 minus 4 is 12. I almost isolated the log term. We just divide both sides by 3, and we get the log of 2x is equal to 4. I may need to pause here for just a second. Okay, sweetie? All right. Yes, I know. You're doing great. I'm so proud of you. Okay. Now I've isolated the log term. I have the log of some stuff involving my variable is equal to a constant. So now I'm going to exponentiate. This is the money step. And before I write it down, I'd like you to think about what base I'm going to use when I exponentiate here. Yeah, that's right, bud. He says we're going to use base 10 because that's the base of this logarithm. And he's right. So we'll get 10 raised to the log of 2x equals 10 to the 4. We put both sides in the exponent of 10. And the magic, of course, is from that property of logarithms, this left-hand side is going to simplify to just the inside here, 2x. So I get 2x equals 10 to the 4, which is 10,000. I had a 10 with 4 zeros, or sorry, a 1 with 4 zeros. And then we solve the resulting equation. So x would be 10,000 divided by 2, which is 5,000. Or about how much I have to pay still on my student loans. Okay, so not too bad, not too bad. Remember, isolate the log first. Don't do any funny business with the log. Just isolate the log. You want to get down to, the goal is to get to a place where you have a single logarithm on the left equals a constant on the right. It could be the other way around. It could be a constant on the right equals a single log on the left. But you want a log, just one log with your variable stuff in it equals a constant. I'm going to pause for a second. All right, we're back. I want to show you a few more examples. This is sort of the simplest non-trivial example, right? Where you actually have to go through all 3 steps. But just like those kind of more exotic examples from the exponential equations where you had to do some algebra work, factoring, something like that, there's plenty of stuff like that here in the land of logarithms. So let's take a look at our first somewhat challenging example. We're going to solve the log of x plus 2 plus the log of x minus 1 is equal to 1. So the challenge here, of course, the isolation of the logarithm it's not immediately obvious how you would do that. Because you've got 2 logarithms, right? And each of them have some variable stuff in them. So it's not like you can treat one as a constant. But we do have a property of logarithms that will allow us to combine these into a single log. And that's one of the reasons why we learned how to combine logarithms. So first here, remember 2 logs added up, as long as they're the same base, can be rewritten as a single log with the insides multiplied. And don't skimp on these parentheses, they're all very important. The big parentheses on the outside here show us what's inside the log and what's not. The little parentheses on the inside are also important because remember we want the log with this times this inside, and each one of those things need to be thought of as a single chunk. In other words, we're going to have to FOIL inside this logarithm, or FOIL at some point in order to figure out what this thing is. And he's rolled off the mat. I got to grab him again. Sorry, guys. Okay, back again. So, like we said, don't skimp on the parentheses. The big parens outside are important because they say what's inside the log and what's not. The little parentheses on the inside are because we're multiplying x plus 2 times x minus 1 using this rule. base a of x times y is the log base a of x plus the log base a of y. That was one of our properties of logarithms. And so here I'm using this property to combine the two logs, right? I've got a log base 10 of x plus 2 plus a log base 10 of x minus 1. So that's the same as the single log base 10 with x plus 2 times x minus 1 inside. From here, I would FOIL inside the log before exponentiating, just to get it out of the way. So this is x squared plus 2x minus 1x is plus x minus 2 inside my log. And all of that is still equal to 1. Now I exponentiate, and again, I'm going to use the base 10 because this is the base 10 logarithm. And that will give me 10 to the log of x squared plus x minus 2 equals 10 to the 1. Remember, we're always exponentiating or taking logs whenever we do either of those on both sides. All right. And the magic here is that the 10 raised to the base 10 log of some shit is always just going to be that shit, because those are inverse functions. That was the immediate consequence of the definition. So this left-hand side is just x squared plus x minus 2. And the right-hand side, 10 to the 1, that's 10. So here we get a quadratic equation after we undo the logs. We had to combine the two logs into one, then we get rid of the log by exponentiating. And this time the result, rather than a linear equation, is a quadratic equation. But we're great at solving quadratic equations. We've had lots of practice with this. We're pretty good at solving polynomial equations in general now. We're going to pull everything to one side. So when you subtract 10 from both sides, this becomes a minus 12, and this becomes a 0. And then we're going to factor. So how can I factor this? Well, I need two numbers whose product is negative 12 and whose sum is 1. Those are 4 and negative 3. So this is x plus 4 times x minus 3 equals 0. And then each of those, this would tell me x is negative 4. This would tell me x is positive 3. So I have two plausible solutions here, negative 4 and positive 3. But before I call it a day, I need to verify that both of those work in the original expression. See, this step where we combine these two logs into this one log changes the domain a little bit. So you need to be careful. If I check x equals 3 in the original, I get the log of 3 plus 2 plus the log of 3 minus 1 is equal to 1. So that says that the log of 5 plus the log of 2 is equal to 1. Everybody is defined and happy here. No problems with negatives inside the log. If there was going to be a problem, it would show up at this first step. This being negative or something. Then of course you get, that's the log of 5 times 2, which is 10, equals 1, which is true. But as long as everything is defined, as long as you don't have a 0 or a negative inside your log, then the solution will work. When we check the other guy, we run into trouble right away. You have the log of negative 4 plus 2 plus the log of negative 4 minus 1 equals 1. And that would say the log of negative 2 plus the log of negative 5 equals 1. And both of those are undefined. right? Because you cannot have, remember, the inside of a logarithm must be greater than or equal to 0. Well, what is true, fun fact, both of those solutions would be fine here, right? Because the -2 times 5, -2 times -5 would become positive inside the logarithm here. But this wasn't the original equation, this was. So we're checking to make sure that both of these solutions work in the original equation. Only 3 works. This guy's got to go, because he makes that original equation undefined in 2 places. Yeah, that's a problem, isn't it, baby? Okay, so you see how important it is to check your answers at the end. And we're beginning to see how some of these logarithm equations can be more involved than the first obvious thing. Okay. I'd like to look at 1 or 2 more examples here just to make sure we've seen enough and we are in good shape. Truth is, these don't really get too bad. I can't think of anything that's really a whole lot more involved than what we just did. Except, when you combine, if you have an equation with multiple log statements, you may combine those multiple log statements. You must combine those multiple log statements. And then that could lead to not just a quadratic equation, but maybe a cubic polynomial equation or a 4th degree polynomial equation, a rational equation, right? An equation involving rational functions, any of those things. You could design a problem that yields any of those things. But we'll keep it mostly simple just to try and keep everybody on the up and up. How about this? Is that exactly the same? Yeah, it is. Okay, that's a little boring. Yeah. How's about? They're all just boring. We'll do this. Let's solve the base 9 log of x minus 5. This is a 9. Base 9 log of x minus 5 plus the base 9 log of x plus 3 is equal to 1. Very similar to the last guy, just a bit more practice. Again, like we did last time, we're going to want to isolate the log. Since there's 2 log terms with variables in them, we need to combine those into a single log first. So following my rule that addition outside is multiplication inside, if the bases are the same, I can rewrite that left-hand side as the base 9 log of x minus 5 times x plus 3. And again, you need to be careful with your parentheses. Both the big parens outside and the little parens inside are necessary. And again, I think it's wise to go ahead and FOIL everything out inside the log before exponentiating. So it's going to be x squared minus 2x minus 15. And all of this still equal to 1. Now we exponentiate base 9. You get 9 raised to the base 9 log of x squared minus 2x minus 15. It's equal to 9 to the 1. Don't forget to exponentiate on the right as well. Nine to the base 9 log of some stuff is just that stuff. So this is x squared minus 2x minus 15 equals 9 to the 1. It's just 9. And again, quadratic equation. We can subtract 9 from both sides. You get x squared minus 2x minus 24, right? Yeah, 24. equals 0. And just like before, now that I have my quadratic equation here, I want to pull everything to one side and factor. In an unpleasant situation, I won't be able to factor. I might need to resort to the quadratic formula. But let's see. I need two numbers whose product is -24 and whose sum is -2. Can I find two such numbers? I think so. 6 and 4 will work, right? The right permutation of signs. This would be x minus 6 times x plus 4 equals 0. So either x is positive 6 or x is -4. And again, one of these is going to cause trouble. Again, it is the negative one that's going to cause trouble, but that's not necessarily the case, right? The trick, the thing to be mindful, it's not that x can't be negative. It's that the inside of the logarithms can't be negative. But here, if I do plug -4 and I get the base 9 log of -4 minus 5 plus the base 9 log of -4 plus 3 equals 1, which is the base 9 log of -9 plus the base 9 log of -1 equals 1. And both of these are undefined. Cannot take any logarithm of any negative number. X equals 6, on the other hand, we should also check, because it's not about the x being negative, it's about the inside of the log being negative. But here I get the base 9 log of 6 minus 5 plus the base 9 log of 6 plus 3 equals 1. It's the base 9 log of 1 plus the base 9 log of 9 equals 1. Pause for a second if you must. What is the base 9 log of 1? It's the same as the base 2 log of 1, or the ln of 1, or the base pi log of 1. That is 0. And the base 9 log of 9, that is 1. So this just says 1 equals 1, which is true. All right. So we hold on to this guy. Throw this guy away. He is what's called an extraneous solution. So that's it. Really, that's the story with logarithmic equations. You're going to isolate the log term, and you might need to use some log properties in order to do that. Then you exponentiate on both sides. Now, come up. Exponentiating on both sides will get you to a place where the logarithms will go away, because the exponential and the log are inverse functions. That'll give you some equation to solve that no longer has logarithms in it. So you will solve that equation using whatever tools you must. If it's a quadratic equation, you want to try to pull everything to one side and factor. If it's a linear equation, you're lucky. You just do the normal thing, right? Most move constants around until you're good. You could get a rational equation, something like x plus 1 over x minus 2 equals 7. And you would solve that the way we solve any rational equation. Pull everything to one side, common denominator, factor, set the top to 0. That's the recipe, gang. That's it. There is a new homework set. I'm going to go ahead and open that as soon as I post this video, and there will also be a quiz. Those are the last things that you need to do before exam 3. Remember, if you are in a Tuesday, Thursday class, exam 3 is going to be this upcoming Thursday. If you're in a Monday, Wednesday class, exam 3 is going to be this upcoming Wednesday. So please take the time to prepare. If you have any questions, you can reach out to me through Discord or coming to office hours or Canvas messages or email. If you have a carrier pigeon, that's fine, but it might take a little bit, whatever you need to do. But please don't suffer in silence. If you're struggling, reach out for help. That's it. All right. Take care again. You want to say goodbye, Johnny man? Let's say hi to my son. Here we go. Whoa. What you doing? Do it. Oh, he's interested in that. That's good. Yeah. Okay. See you later, guys.